Okay, cool. Oh yeah, I wanted to just finish this one. Okay, so to finish this one, here's the deal. I'm going to set up an integral. And again, the function we're integrating gets turned into t's via the parameterization we chose. So this is going to be a t, but since y is 0, that's just a 0. And so now I need the ds. Okay, well, again, I had a formula for ds up here a minute ago. It was, the square root of x prime squared plus y prime squared. Again, from this parameterization, x prime is simply a 1, y prime is a 0. So here we go. The ds is very cool and easy here. ds is the square root of 1 squared plus 0 squared dt. Or in other words, ds is dt in this problem. ds is dt in this problem. And we're going to integrate from 0 to 2. So this is us doing this line integral for, 1/4 of this problem. We just did C1. Well, if I'd finished this integral, I've done C1. So what do you have to do? You have to parameterize the curve, and you got to find ds. You got to parameterize the curve, put those into the function, and you got to find ds. Here, we'll finish it. It's easy. T squared over 2. T squared over 2 from 0 to 2. I think that's 2. So that's C1. I got to do 3 more of these. Let's work on C2 here a second. C2. A parameterization for C2. I need x and I need y. Well, this time I think y is varying. I want to call y t. And I think x is stuck. I think x is stuck on 2. So x is 2. That's my parameterization for this line right here. Oh, and t is going to go from whatever y does, which is 0 to 2. These were all 2's here. From 0 to 2. Cool. T goes from 0 to 2 again. I need ds again, which means I need x prime again. X prime is a 0. Y prime is a 1. I need the ds again, which is the square root of the 0 squared plus the 1 squared, which is 1 again, 1 dt. ds just is dt. So anyway, I just set that one up quick. Well, I didn't set it up. Here it goes. It's 0 to 2. What am I doing this time? Oh yeah, this function with the x and the y replaced. Okay, that x is a 2. That y is a t, square root of t. Okay, ds is just a dt. And we said 0 to 2 because that's my values for t. Okay, this one takes a little more work. You integrate and you get 2t. Of course, this is t to the half. When you integrate, it's t to the 3/2. T to the 3/2 times 2/3, where the 4 out front would be 8/3, I think, from 0 to 2. Yeah, from 0 to 2. Cool. Plug in your 2. 4 plus, oh my goodness, 8/3. Plug in that 2. It's the square root of 2 cubed. The square root of 2 cubed is 2 square roots of 2. Oh well, this is my answer for the second integral. This second little piece is, got this answer. 4 plus 16/3 square roots of 2, I guess. That's my answer for C1. This is my answer for C2. For integrating this function along C1, for integrating this function along C2. In the end, I got to add all these answers up. Let's do C3. Let's see what's going on with C3. I mean, this is starting to get a little boring, but all of a sudden, C3 is going backwards, if you can tell. C3 is moving this way. I got to parameterize this way. Now, let me think. My first instinct is x is moving. I want to let x be t. I want to let x be t. I think y is stuck on 2. Y is stuck on 2. The problem with that is it's going backwards. So could I tell it I want t to go from 2 to 0? I don't think I'm allowed to do that. Not with these problems. I don't think I'm allowed to do that. I don't think I'm allowed to say t goes from 2 to 0. That would work, but then my integral would be going from 2 to 0. My integral is kind of backwards. I don't think I'm allowed to do that. So I want my time to go forward. Instead of from 2 to 0, maybe I should go from 0 to 2. Now, how am I going to do that? Wait, so I want, I'm trying to do C3. So when t is 0, I want x to be here at 2. When t is 2, maybe, I want x to be over here at 0. Jesus, I don't know if that helps me. But I have some experience. I think this might, what if I just put a negative t, does that work? No, and then try to go from, hang on, and then try to go from 0 to 2? See, that doesn't work. That goes from 0 to negative 2. That doesn't, I'm trying to go, what am I trying to do? I want x to go from 2 to 0, while t goes from 0 to 2. And I put a negative t on it, that doesn't really work. I think this does, though, and I figured it out. Watch this. How about 2 minus t? I think that works. Because when t is 0, x is 2. That's what I want. And when t is 2, x is 0. That is what I want. That's what I want for a backwards moving x like that. That's what I want. Wow. Hey, I'm going to need x prime and y prime. X prime is -1. Y prime is 0. I need that for the ds, which is the square root of the x prime squared plus the y prime squared. You know, despite that being a -1, by the time you square it and square root it, it's still just a 1. So again, ds is just a 1 dt. I need the parameterization. I need the derivatives to calculate this ds thing. And now I'm ready to set up the integral. I think the bounds are 0 to 2. And x, where am I doing? Hang on, what am I doing? I'm doing this integral, the same old integral. X is now replaced with what it is on the curve. X is a 2 minus t. And y is replaced with what it is. That's a 4 square root of y. 4 square root, but y is just a 2. And then out on the end is your ds, which is just your dt. Cool. This ain't too bad. That's a number. That's a number. That's a variable. I can integrate this. This is 2t minus t squared over 2. And then when I integrate that, that's at 4 square roots of 2t. From 0 to 2, I'll plug all my 2's in. I'll be good. This is 4 minus 2 plus 8 square roots of 2. When you plug in your 0, this is all gone. So we're done. That was awesome. This is a 2 plus 8 square roots of 2. Wow. This is still one problem, right? Number 18. What's making it so difficult? I have to do C1, C2, C3, and now C4. What a pain. As you can tell, they're all pretty easy though. C1, C2, C3, and C4 are pretty easy. Little individual dudes. But they all have their own little twists and turns you got to think about. Let's try one more. Let's try C4. I need a parameterization for C4. C4 is this. Again, right up here, y equals 2, and then I'm headed to y equals 0. I think I want that to start at a 0 and go to a 2 for t. By the way, that's y moving. I think x is stuck. X is stuck on 0. And y is moving, but it's moving backwards. And I think I'm going to employ the same idea I had with C3. I think I'm going to call y 2 minus t. 2 minus t. And then let t go from 0 to 2. Because when t is 0, y is 2. That's exactly what I want. And when t is 2, y is 0. Yeah, that's exactly what I want. Here we go. Let's find x prime. X prime is a 0. Y prime is a negative 1. Oops. Y prime is a negative 1. That helps me find ds. Similar to the last problem, ds is just going to be a 1 dt again. Here I go. I set up the integral. The bounds are 0 to 2 for t. And we plug in the 0 for the x, so that's just a 0. I'm integrating this 4 times the square root of y, and y is a 2 minus t dt. Wow, that's a hell of a problem. Let's finish it. I'm going to talk fast here at the end to try to finish this problem. I integrate. In order to integrate, I got to do u substitution. If I do u substitution, it's going to spit out a negative sign. The answer is going to be a negative 4. Hang on. It spit out a negative sign. Then it's u to the 1/2. So when you integrate, it's u to the 3/2, or 2 minus t to the 3/2 times 2/3, times 2/3. I just integrated. I did u substitution. It's u to the 1/2. It's u to the 3/2 times 2/3. It spit out a negative sign, and I need to evaluate from 0 to 2. Here we go. Plug in a 2, and you get a big fat 0. Minus a negative 8/3 times, when you plug in your 0, 2 to the 3/2, which is 2 square roots of 2 again. That's interesting. This is positive 16 square roots of 2 over 3. Whew. To finish this problem, I got to add up my 4 answers. What are my 4 answers? 2, 4 plus 16/3 square roots of 2. What was that answer? What was that answer? 2 plus 8 square roots of 2. And now finally this answer. 16. I did these fast. I hope I did them right. So this is the answer. Add these guys up. That's an 8. And these are 16/3, that's 32/3, 24/3. That's 56/3 square roots of 2. Good God. I don't even know if that's the right answer. That was fast work. It might be the answer. You can double check me in your leisure. You can double check me in your leisure. Those were easy little curves, but I had to do 4 of them. What a pain in the butt. So that happens in this chapter. All right, look, I want to, we're almost at the end of class, but I got started a little late. I'm going to keep talking here a little bit. I want to do one more problem. I want to get rid of this one. So we're talking about these line integrals. And we've just sort of talked about this one type, which is integrating a function with respect to the length of the curve over which we're integrating. We're integrating a function over a curve. It's called a line integral or a curve integral. And we did 2 or 3 examples. But the more important version of a line integral, now this is on your test, this is decent, but we're about to abandon this, and I don't want to do too many more of these, because the more important part, the rest of this chapter, is about this line integral. This line integral is this one. It's also introduced in 15.2. This is still in 15.2. But notice this. This is another line integral, but this time I'm integrating over a curve. I'm integrating a vector field over a curve and dot product with the derivative of the curve. I'm integrating f dot dr, these are vectors, I'm integrating this dot product over the curve. What this is, this does have some meaning. This is the work, and that's the physical term for work, which is an energy. The work done by the vector field. This is the work done by the vector field F on a particle as it travels. The work done by the vector field F on a particle as it travels through the vector field F on the path or curve C. Wow, this is cool. This is physics. Work is energy. Work is a force times distance. Perhaps that's what this is. This force field, this vector field is a force field, and we're multiplying by this distance. Is that a distance? I guess that's a distance. Yeah. So a second type of line it has nothing to do. There's no ds. It's different. It's no ds. It's no f of x, y. This is different. I'm dealing with these vectors. A lot of similar properties. We have to parameterize the curve. We have to do a lot of similar steps like we did in that one, but it's a totally different integral. Let's do one, and then we'll quit here. Let's do one. What do I got to do? I got to give you a vector field. Let's say we're doing this vector field. Let me see. I might just grab one of these out of the book here. Let me see if I do this vector field. X, okay, xy comma y, and I'm going to go on this curve. The curve is r of t. Now instead of, okay, a different way of parameterizing is using this vector valued function. R of t is 4 cos t, comma 4 sine t. I just grabbed this problem out of the book. This happens to be number 28. And then they say from t goes from 0 to pi over 2. You know, again, to make you think a little harder, maybe a better way for me to talk, maybe I would have liked to give you the picture of this. Maybe I would have said, oh, this is a semicircle, or not quite a semicircle, a quarter of a circle of radius 4 that goes from here to here. If I told you this was the curve, it'd be your job to say, oh, dude, that's a circle. If it's a circle, I should parameterize it. It's radius 4. I should parameterize it like this. 4 cos t, 4 sine t. And if you're only going a quarter of a circle, of course, the amount of t you need is 0 to pi over 2. So maybe, you know, I give you the picture and make you parameterize it. That's what I like to do. But this one, they kind of gave it to me already, parameterized. I'm describing it to you. And now, how do we do this problem? It's a little different. We don't need the ds. What we need is the dot product of f dot dr. But we still turn everything, we don't deal with x's and y's. We turn everything into t's. So here I go. I'm setting up the integral. And since I know it's going to be in t's, that the whole integral is going to be in t's, I think those are my bounds. 0 to pi over 2. Now, what am I integrating? Okay, the vector field. Okay, well, there's the vector field f. But I have to replace those x's and y's with what x and y are on the curve. So there's my x, and there's my y, of course. So here I go. That's x times y. So that's x, that's 16 cos t sine t, comma, and then here comes y, which is 4 sine t. Okay, there's my vector field. It's the same old vector field I had, just put into t's. Bless you. dot product dr. Okay, now dr is not r. Dr is the derivative of r. I mean, it's kind of like dr dt. And what would be the derivative? Okay, the derivative with respect to t. Derivative of cosine is negative sine. So negative 4 sine t, comma, derivative of sine is cosine 4 cos t. You know, the formula says it's f dot dr. Okay, so just watch this. So dr is, when you take this dt and multiply it over to the other side, then dr is the negative 4 sine t, comma, 4 cos t with the dt out here. So this is beautiful. You are integrating with respect to t, just like you're supposed to, but you have to integrate this dot product. How do you do that? Well, you do the dot product. The dot product turns into a scalar, and you integrate the scalar function. You do the dot product, and it turns into a scalar that you integrate. Here we go. Here we go. Here we go. The dot product. Oh my God, this might be tough. That's negative 64. Wow. Negative 64 cos t sine squared t. Oh my goodness. Plus this thing. 16 sine t cos t plus 16 sine t cos t dt. Okay, that's good. You know, now I got to integrate, which, you know, sometimes that's the challenge. I mean, all this stuff is a challenge. Here I am finally. I did the dot product, and now I want to integrate. Yeah, this is kind of a funny one, you guys. I'm going to do something a little funny. I'm going to do this. I am going to factor out a cos t out on the back end of this. So that leaves me 64 sine squared t plus 16 sine t. And so what did I say? I'm factoring out a cos t out here on the back end. Is that what I did? I factored a cos t and a cos t out here on the back end. And that leaves me with that. Yeah, that's beautiful. Because now I can let u equal sine t. The derivative of u, the derivative of sine t is cos t dt. So this is awesome. I just turned out, I mean, in order to finish this integral, I need this u substitution. And I just turned this into negative 64 u squared plus 16u. Because I let u equal sine t, and du was cos t dt. So there's your du. And so here you are. This is not hard. Let's integrate. 64 thirds u cubed plus 16 halves u squared, 8u squared. Let's plug back in what u is. U is sine t. Negative 64 thirds sine cubed of t plus 8 sine squared of t. Wow, dude. That's tough, but we're done. We integrated. U substitution helped me out. Factoring that out helped me. It helped me do one problem instead of two problems is what it did. Now what? Evaluate from 0 to pi over 2. Sometimes these things are kind of anticlimactic. Sometimes in the end you just get a 0 or something funny. This one ain't bad. Let's see. Because when you plug in pi over 2, the sine of pi over 2 is a 1. So I'm getting a 1. Sine of pi over 2 is a 1. So I'm getting negative 64 thirds plus 8. Negative 64 thirds plus 8. Minus, plug in the zeros. When you plug in the zeros, the sine of 0 is 0. So we're finished. This is negative 64 thirds plus 24 thirds, which is negative 40 thirds. Wow. All right, we're done. I want to make just a couple comments. We're done. We did a hell of a, we did this. What did we find? We got negative 40 thirds. That is the work done by the vector field on a little particle as it travels through the vector field along this curve. What was the curve? The curve was this, and the vector field was this. So what you can't see is that, and it'd be cool to see, but this is traveling through a vector field. And if I plotted some vectors, I could, maybe see that I've got a vector field that I'm traveling through. Now, the reason I'm drawing these vectors sort of this way is because the answer came out negative. And so I think what was happening is we were primarily going against the vector field. Our travel was against the vector field. That's why it came out as negative work. That's fine. It's allowed. These answers can be 0, positive, or negative. So we're done. Thank you. Do some 15-2 homework.